Okay, and welcome back. Today we're going to have a look at section 3.5 on implicit differentiation. So the idea here is that we have two or more variables happening at the same time. So we'll start with one that we can do two different ways. We'll look at the equation y to the 7th is worth x. So the way we would typically have done this in the past, if we want to differentiate this, is solve for y. So that in this case, a 7th root of both sides will do the job just fine. Since it's an odd root, we don't need the plus or minus, so y is just x to the 1/7 power. So then y prime, no problem, 1/7 x to the negative 6/7. Now, it is possible to do this a different way, and this is relying on what you did last section with the composition problems. So here, y is a function of x. So one option is to simply differentiate both sides with respect to the variable x. So the left-hand side, if I'm differentiating y to the 7th, I have 7, y to the 6th, just general power rule stuff. But again, y is a function of x. X here is the independent variable. So we have to multiply by dy dx as well. So this is equivalent to our g prime of x in the problems in the last section. Right-hand side derivative of x is still just a plain 1. So dy dx is 1/7 y to the negative 6th. I think you might be able to hear my 8-month-old in the background there. It's all right, she's doing fine. And here with substitution, you can get the same thing back here. So y here is x to the 1/7. So x to the 1/7 to the negative 6 does get us back to that x to the negative 6/7. So they are equivalent to one another. Now, it's not always practical, and sometimes, in fact, is even impossible to solve for y. So that's why you might notice if we can solve for y, it's a little bit quicker, easier to do. If the functions get a little bit more complicated, then we do want this implicit differentiation. So this next one we'll look at is the graph of a circle, cap f of xy. So we're treating x and y as our inputs here. It's going to be x squared plus y squared, and we'll set that to 36. So hopefully you recognize that from your college algebra days. This is a circle of radius 6 centered on the origin. Well, with that in mind, and I'll just draw a very quick, rough sketch with a lot of imagination. That's a circle of radius 6 on the center. But at any one x value, we might have two different rates of change happening depending on which y value we're at. So if we're looking to differentiate that, in this case, we'll still find dy dx. We're going to differentiate both sides of our equation. So derivative of x squared is still just 2x. Derivative of y squared is 2y times dy dx. You may want to do that in red or underline it, highlight it, do something to remember it. This is the key to that section. Anytime you're differentiating something other than the variable at the bottom here, you're going to attach one of these. The other side, derivative of a constant, is always 0. So dy dx is negative 2x over 2y. So subtract 2x on both sides, divide both sides by 2y. You can do even a little simplifying there. Dy dx is then opposite of x over y. So notice it depends not just on the x value, but also the y value. So they may ask us not just to find dy dx, they might ask us for the slope at different points. We'll just do at x equals 1 for now. So you should see we do have 2 of those. We know an x value, we need a y value. dy dx depends not just on the x, but also on the y. So we just go back to the original. So x squared, 1 squared, plus y squared is worth 36. So y squared is 35. So y is plus or minus root 35. So when x is 1, we have 2 y values, so 2 different slopes. So dy dx in one case would be opposite of x, so opposite of 1 over y. One of them will be over root 35. So negative root 35 over 35. So that one is at 1 comma root 35. dy dx at our other ordered pair, opposite of x, so opposite of 1 over negative root 35, 1 over root 35, or just root 35 over 35. And again, that is at 1 comma negative root 35. So what the slope is depends on where on the graph we're looking. All right. So this next one, they're going to look for the tangent line at a given point. But really, that's just building off of things we've already done. So now they're looking for the equation of the tangent line at x equals 3. So they'll give us, in this case, the equation x squared plus 5xy plus y squared plus 41 plus 41 is equal to 0. So tangent line, we're thinking derivative. So derivative, in this case, we're thinking dy dx. So I'm going to differentiate both sides. Derivative of x squared is just a plain 2x. Careful here, this is a product rule. So plus derivative of the 5x is just 5. That's our first factor. Second factor is y. We keep the second factor. Product rule, so it's followed by a plus. Then we keep the first factor 5x and multiply by the derivative of y, which is 1 times dy dx, or just dy dx. So there's our product rule happening in the middle there. Next term, a y squared. Derivative of y squared, 2y times, don't forget your dy over dx. Derivative of a constant is 0. Derivative of 0 is 0. So after that, our idea is we want to find dy dx. Well, just solve for it. So here's a couple of terms that did not have dy dx. We'll move those. And we'll go ahead and factor dy dx on this side. So 5x plus 2y each had a dy dx attached, so we'll factor that. And 2x and the 5y got moved to the right-hand side. So for this one, dy dx, negative 2x minus 5y all over 5x plus 2y. We can't cancel any of those 5's, 2's, x's, or y's because we don't have any common factors other than the trivial 1 or negative 1. Okay, so that's just part of the question. Remember to kind of glance back periodically, make sure you're answering the question that they asked. They want the equation of the tangent line at x equals 3. Well, notice that the slope at x equals 3 depends both on the x's and the y's. So we're going to have to find our y values when x is 3. So a little substitution in the original. Anytime you want ordered pairs, the original is where you're going. So plugging in 3 into the first term, we have 9. 3 for x in the second term, we have 15y. We don't know a y value yet, so we keep our y squared and plus 41, and we're still equal to 0. So reordering, y squared plus 15y plus 50 is 0, and that's factorable over the integer. So y plus 10 by y plus 5 is 0, so y is negative 10, or y is negative 5. So we're going to have two equations because we're going to have 2 points which will have one tangent line each going through them. All right, so basically our ordered pairs, we have 3, negative 10, and we have another one at 3, negative 5. So our slope for the 3, negative 10, dy dx, subbing in 3 for the x and negative 10 for the y. So 3 by negative 2, negative 6. Negative 5 by negative 10 is positive 50. 5 by 3, 15. 2 by negative 10, negative 20. So we have 44 over negative 5. So there is our slope. So then just change in y is slope times change in x. So y minus a negative 10 turns into y plus 10 is our slope, negative 44 fifths, times our change in x, x minus 3. So y is negative 44 fifths of x plus 132 fifths. And then I'll subtract 10, which is 50 fifths. Y is negative 44 fifths of x. And then plus, let's see, 82 fifths. So there's one of our two tangent lines. This is the tangent line through 3, negative 10. This is an equation, but not a function. We do have one other ordered pair when x is worth 3. So first we'll figure out what the slope is at that point. So again, we go back to our dy dx. X still is a positive 3, so we have negative 2 by 3, still negative 6. Y this time is a negative 5, so minus 5 times negative 5 plus 25. And downstairs 5 by 3, 15. And 2 by negative 5, negative 10. So that would be 19 fifths. So this one has a positive slope. So then change in y minus negative 5 turns into y plus 5 is our new slope, 19 fifths times change in x. And then same deal, distribute the 19 fifths. And I'm going to subtract 5, which is 25 fifths. So y is 19/5 of x. And let's see, so minus 82/5. So there is our second tangent line. So we have two tangent lines for the price of one. Now occasionally our input variable will be a t and our output variable will be an x. So different notation, but same idea still. So they might ask us to find x prime of t. For the equation t squared times natural log of x is worth x e to the t minus 1. So same idea, we're looking to differentiate this function, only now we're treating t the same way we used to treat x. X is getting treated the same way we used to treat y. So left-hand side, hopefully you recognize that as a product rule problem. So two factors. My first factor, t squared, we're going to differentiate that. So that would be 2t times, keep the second factor, natural log x, plus, and then they trade roles. So now I'm going to hang on to the t squared, and we'll differentiate natural log of x. Typically, we would just call that 1 over x, but this time again, t is my independent variable, so I have to multiply by dx dt. We're eventually going to replace that with an x prime of t. So right-hand side, another product rule problem happening. So derivative of x, usually just a 1, but again, x is no longer my independent variable, so times dx dt. And we keep the second factor e to the t. So product rule happening again. Derivative of x, keep the second factor, plus trade roles. Now I'll hang on to the x, differentiate e to the t, which is still just e to the t. All right, so the goal is to find the dx dt. I've got them on both sides, so let's fix that. Move them onto one side. All the terms that don't have dx dt, move them to the other side. So we have, let's see, left-hand side, I'll keep this t squared over x. And I will move the e to the t. So minus e to the t. Each of those had dx dt. So that meant that this guy stayed put, x e to the t stayed where it was, and this guy moved to the other side, so minus 2t natural log x. All right, so we're going to end up dividing next, but we don't want a fraction within a fraction. So we'll go ahead and multiply both sides by x to clear that out. So now we have t squared minus x e to the t quantity times dx dt. It's worth x squared e to the t minus 2 dx natural log x. So now we're ready to divide. So dx dt, x squared e to the t minus 2t x natural log x, all over t squared minus x e to the t. So there is our derivative. There is our x prime of t. So we kind of switch to that notation once we're done doing the operations. And they could ask us to evaluate at different points. So we'll evaluate x prime at t equals 0, x equals, let's say 1. And you can see that that does check out. 0 squared is 0. Natural log of 1 is also 0. 0 on the left side. 1 times e to the 0. E to the 0 is 1. 1 times 1 is 1. And 1 minus 1 is indeed 0. So that ordered pair does check out. So then our x prime is equal to x squared. So 1 squared is just 1. E to the 0 minus 2 times 0 times, doesn't really matter what else, so 1 and a natural log of 1 over 0 squared minus 1 e to the 0, x prime. 1 times e to the 0 is 1. 0 times anything is 0. 0 squared is 0. E to the 0 is 1. 1 times 1 is 1. So negative 1. If they ask for a tangent line, zero, 1, remember on these, it's t comma x this time. So then change in output. So instead of y minus something, it's x minus something. So x minus 1 is our slope times input variable is now t minus 0. So x is opposite of t plus 1. Okay, so that should give you enough information to try out the problems in section, this is 3.5. If you're in the new edition, 1 through 41 odd, 45 to 51 odd. If you're working with the older book, 1 to 37 odd, and 41 to 47 odd. Okay, so stay safe. Hope to see you soon. Email me with any questions.